So something like this, let's say. So something that has maybe two batteries, a capacitor, but a complex system of resistors and capacitors. So how can we find out the charge of the capacitor as a function of time and the current, the charge of the capacitor as a function of time, and then the current as a function of time for each of these three resistors? So if we call this resistor 1, resistor 2, resistor 3, I1, I2, and I3 as a function of time, you see, and then the charge of this capacitor as a function of time. So let's give this some numbers. Let's say 20 volts. So let's say 6 kilo ohms. Maybe this is 8 kilo ohms. Let's say this is 4 kilo ohms. And let's say this is 8 volts. And let's say this is 2 millifarads. So also solve for the time constant of this circuit. What's going to be the time constant? Remember how it's RC, but in this case, which R is it? Is it all the R's? Is it only this R? Because the C is here, right? Well, in solving these equations, you will have solved what the time constant is, you see. So that's kind of a byproduct. So how would you approach something like this? So what you do is do the Kirchhoff's loops. You just do like, let's say you do 2 loops. Let's call this current here I1, and I'm going to call this current I2. Now, in this problem, I'm going to assume the charge of this is initially 0. But you could also do where it has an initial charge other than 0. So change the initial condition again, you know. But let's do initial charge 0. So this is going to call, I'm going to call this guy I2. And then this one here will be I1 minus I2. Okay, so then let's see here. You have here, if I do the left loop, I gain 20. I lose here 6I1. And then here I lose 8I2. And then here I have minus Q. Well, you know what? Let's just say, could we keep this as a kilo? Could we just say it as a 6? Yeah, I think it's okay. I think we can just keep it as a 6. Later on, we'll interpret where the kilo and the milli will go. Okay, so then I'm just going to say here minus the charge of this guy, which is Q2. So you see, the reason I call this one I2, the current going through here, is because I can just easily say the charge that builds here is Q2. You see, so then that makes it easy. Q2 over C, and C is 2 millifarads. But I'm going to just keep it as 2 and then deal with the milli later on. Q2 over 2, and then you come, and then that's 0. You see, and then the other circuit is, I'm going to make it the whole thing. You see, so let's just simplify this. 20 is equal to 6I1 plus 8I2 plus Q2 over 2. Multiply everything by 2. 40 is equal to 6I1 plus 8. No, sorry. 40 is equal to 12 I1 plus 16 I2 plus Q2. Okay. Okay, so then that's our first equation. So now do the full loop, and you get 20 minus 6I1, and then you get minus 4I1 minus I2 minus 8. And then that's it. And that's equal to 0. And then so 20 minus 8 is 12. And then it is 6I1 plus 4I1 minus I2. Okay, so then you're just going to have 12 is equal to 4I1 plus 6I1 plus 4I1, 10I1, right? 12 is equal to 10I1 minus 4I2. Okay, so here's my next equation, right? Cool. So 10I1 minus 4I2. Now here's the next step that we can do. We could get rid of I1 here. Because if I can get rid of I1, then I'll just have an equation with Q2 and I2. You see? So I could say 10I1 is equal to 12 plus 4I2 over 10, and then divide by 10, right? So I1 is going to be 12 plus 4I2, right, over 10. And then substitute that into the I1 here. So you see 12 plus 16. So then you're just going to have 12 plus 4I2 over 10 plus 16I2 plus Q2. Okay, nice. Multiply everything by 10. So then you're going to have 400 is equal to, okay, then the 10 will disappear. 12 times 12 is 144. 12 times 4 is 48. And then 10 times 16 is 160. 10 times Q2, 10 Q2. Okay. And then 400 minus 144, 256. 48 plus 60, 208. Plus 10Q2. Okay, so we've got our differential equation right here. If I divide everything by 2, 256 divided by 2 is going to be 128. This one divided by 2, 104. So this is your 104 dq2 dt plus 5q2. So I can then steal the result that I have from the previous differential equation. What was that differential equation? When we first set up the Oh, okay. So you see, when we first set up the differential equation, we have VB is R dq dt plus 1 over C. And then the solution to that is some constant A, e to the bt plus D, where B is equal to negative 1 over RC. Okay, so for the regular equation, we have something like this. VB is equal to R dq dt plus 1 over CQ. And then the solution to that is going to be some constant A, e to the minus T over RC. Actually, I don't even need the constant A because we're assuming the charge here is 0, the initial charge. So I can use the result, the final result that I got, CVB 1 minus e to the minus T over RC. So in other words, to this kind of differential equation, the solution is this if the initial value of that function is 0. Okay, so then this is my differential equation. So if I'm assuming the initial charge of the capacitor is uncharged, the Q, so then let's see here. So my R will be what? Well, you know what? I could divide everything by yeah, I could even divide everything by 5. And then I could look, it looks like this. 128 over 5 is equal to 104 over 5 dq dt plus q2. Okay, so in my case, what's my C value, right? It's just 1, right? Because I've divided everything over. So then this is gone. So my C value is 1. Okay, what's my R value? It would be whatever's in front of this dq dt, right? So my R value is 104 over 5. And then what's my VB value? Then my VB value is this. So you see, I'm making it look like this differential equation, although it doesn't necessarily have to have something down here. It could just have a 1. You see, then this I will be guaranteed that this will be its solution if the initial charge is 0. So in my case, what's going to be the solution of the QT? C in my case is 1. So VB is what? Is this guy, right? 128 over 5. 1 minus e to the minus T over, and then my RC. So then this is my R, 104 over 5, and then my C acts like 1 in this case. You see? So now once I have the equation for the charge of the capacitor, everything kind of falls into place, right? If I know the charge of the capacitor, what could I do? I could differentiate that to get the I2 as a function of time. I2 is going to be simply the derivative of that. What's going to be the derivative of that? Let's see, when you take the derivative of that, well, the 5 can kind of go over there. So take the derivative, it's going to be 5 over 104 is going to come out, right? 1 over 104. Yeah, it's going to be 5 over 104. So then e to the minus 2 over 104 over 5. So it's going to be 128 over 104 e to the minus t over 104 over 5. So that's going to be the current I2. Then what's going to be the current I1? right? Well, then I1, I could use the fact that it was 12 plus 4I2 over 10, you see. So then I can add 12 plus 4 times this over 10. So you see, everything kind of falls down as a puzzle after that. So now I can find out the values of each of these at any particular time, you see. So if it says, okay, what's the time constant? What is it going to be? My time constant is going to be, well, whatever was here, right? What's my time constant? This is my RC value. You see, the 104 over the 5. Well, because R was 104 over 5 and C was 1. So this is my RC, 104 over 5, which is going to be how many seconds? 20-something seconds? 104 over 5. 20.8 seconds. Does that make sense? 20.8 seconds. Can you get that just by looking at this? The RC. Well, you only have one C, that's 2 millicoulombs. Do these two resistors act like parallel? Well, you have a battery. If you were to argue that these two resistors act as in parallel, what would the net resistance be? You see, what I'm trying to do is say, could we have guessed this 20.8 for the time constant just by saying these two are in parallel? What would their net resistance have been? 1 over R prime, 1 over 8 plus 1 over 4. 3 over 8. So R prime would have been 8 over 3, right? Then add that in series with the 6. Our total would have been 6 plus 8/3. So then would the RC have been the total resistance times that C? I don't think so, huh? This is 6 plus 8/3. 6 plus 8 over 3 times C is 2. 6 plus 8 over 3. So if you take total resistance is this times that capacitance, 17.33. You would have thought that the time constant is 17.3, but it's actually 20.8. Okay, so you've got the Q and I2, but so you see, you can kind of get any value. So let's say I want to find out the value at t goes to infinity. So way at the end, when you have charged this, what are the values of each of the currents and the charges and the voltages and all of that? But I could do it at any time, of course. Once you derive this, I could say, what are their values at 10 seconds, at 2 seconds, or whatever. But infinity is kind of nice because it shows you the behavior of a circuit when you have it connected, when it's been connected for a long time. That's always nice to begin with. So find all the values at infinity. And by infinity, we mean the circuit has been connected for a very long time. So what's going to be the QC? Okay, e to the minus infinity. So this is drops to 0. So this is the final charge of the capacitors. And of course, now we can attach the millicoulombs. So let's write down all the values at infinity. once we've got this equation, we can figure out all of them. So as t goes to infinity, QC is 128 over 5. Once I know QC, I could calculate what the voltage of the capacitor is, right? I just divide the QC by C. What was my C? 2 millicoulombs. So divide this by 2, you get 64 over 5 volts. Which is what? 12.8 volts. Okay, then let's take the derivative of it, I2, which is this function, and then take that as t goes to infinity. Infinity. Well, e to the minus infinity is 0. Oh, I2 drops to 0. Now see, I2 goes to 0, which means the voltage of the resistor 2 goes to 0. Okay, so you see what it's telling us? That means at the end, when it's been connected for a very long time, this is going to be 12.8 volts, but the voltage across this is going to be non-existent. There's going to be no current there. Does that make sense? So when it's been charging for a very long time, what happens? The charge across that element where the capacitor is should have no longer any more current when you approach infinity. You see, so that does make sense. And then the voltage there reaches 12.8 volts. And then that current is 0. Okay, now we can calculate the rest of the currents. What's I1 then? I1 was 12 plus 4I2 over 10. So if the I2 is 0, what would I1 be? 12 over 10, that's 1.2 amps. So I1 approaches 1.2 amps. Okay, which means the voltage of this resistor, if this is 1.2 amps, the voltage is 6 times 1.2. 6 times 1.2, 7.2 volts. Okay, then what's left is to do I1 minus I2. You see, so well, but if the thing is, if I2 is 0, then that's just I1. Right, so then I1 reaches what? Also reaches 1.2 amps. See, and then no, sorry, not I1. The I1 minus I2 reaches 1.2 amps, and then the voltage across that reaches what? 4 times that is 4.8 volts. So at the end, the circuit looks like this. So on the test, when you get this, hint, hint, right? That's one thing to check, is check to see if your answer makes sense at the two end extremes, at infinity and at the initial time. And then if that makes sense, then you can answer any other question. So at infinity, the current here is 1.2 amps, no current here, and then this is also 1.2. So it's almost like this part of the circuit doesn't exist. The voltage across here is 7.2 volts. The voltage across here is 0. The voltage across there was what? 12.8 volts. 12.8. And then the voltage across here was 4.8. And then, of course, this is, was it, what was that battery? 8 volts. So does that make sense? if I do any loop, the potential gains and losses should be 0, right? 20 minus 7.2, right? Then you go down nothing here, and then 12.8, right? Well, is that 0? 20 minus 7.2 minus 12.8. Yeah, happy face, right? And then 20 minus 7.2 minus 4.8 minus 8 for this side. And then that's also going to be 0. Nice. And does it make sense there's no current here in the part of the circuit where the capacitor is? Yeah, because the capacitor is charged. So it almost behaves as if it's not even there. You see? How about at t equals to 0? What are all the values? At t equals to 0, when you first connect them. So then you do the opposite. You say 1 minus e to the 0. Okay, so the charge of the capacitor is 0. Voltage of the capacitor is 0. Then what's the initial current? I2. You put e to the 0 here. What are you going to get? For I2, e to the 0 is 1. So the initial current for I2 is 128 over 104. And so that it looks like this then at t equals to 0. God, this is amazing. It's so awesome. So at t equals to 0, this is 0. Zero volts. This is 8. So the current here is going to be that value. Then if I want to know the voltage drop there, I'll do this times the resistance. What was that resistance? 8. Mm-mm-mm. 8 times 128 over 104. Okay, so the voltage drop here is 9.846 volts. And the current (1.2307 amps). So initially, the capacitor acts as if it's not even there. So it kind of behaves like this kind of a circuit. I think then maybe you could kind of say, oh, it acts like parallel. Yeah. Okay, so then what's I1 going to be? Remember, I1 was, what was the general equation? 12 plus 4I2 over 10. 12 plus 4I2 over 10. So then if I take this I2, 12 plus 4 times 1.2307 divided by 10. Okay, so this is I1 is going to be 1.692 amps, right? And of course, I2 was, so this is the voltage, and then I2 was how many? 1.2307. So then, of course, we could determine the current here, just subtract those currents, minus 1.2307, 0.46158 amps. Okay, so You've got the current there, you've got the current there. The voltage here is 98 volts. Now let's do the voltage there. What's the resistance there? 6. So multiply 6 by there. 6 times 1.692. Okay, so the voltage 10.152 volts. And then here it's going to be 4 times that. .846 volts. Here we go. Let's do our loops. 20 volts minus 10.152 minus 9.846, and then nothing across the capacitor, because that's when you first connected it. There's nothing on the capacitors, right? So is that equal to 0? Yeah, it should be. Yep. Happy face. Okay, and then the big circuit, 20 minus 10.152 minus, you go down this way, 1.846 minus 8. Yeah, that should be right. Yeah, because 1.846 minus 8, that's 9.846. Yep. Yeah, so this differential equation method is really good. That means that our equations are all making sense. This equation, right? And now I can answer any other question, like at t equals to some number, what are the values of the voltages of each, and the currents in the circuit, right? Okay, guys, that's it for today. The chapter is done.